This videocast is about electron configuration. So we're going to use our quantum numbers to describe the most probable location for an electron. This videocast is only going to include the first two quantum numbers, the energy level and the sublevel or the shape of that orbital. The first is a table where we're going to discuss the energy level, the maximum number of electrons available for that energy level, and which sublevels are on each energy level. Energy level 1, you may have remembered from middle school when you looked at the atom before, can hold a maximum number of 2 electrons. It only has an s sublevel, which is the shape of a sphere. Energy level 2 can hold a maximum of 8 electrons, and it has its own s sublevel and a p sublevel. The third energy level of an atom can hold a maximum of 18 electrons, and it has its own s sublevel, its own p sublevel, and a d sublevel. The fourth energy level can hold up to 32 electrons. It has its own s, it has its own p, it has its own d, and an f sublevel. As you go more than 4 energy levels, they're going to replicate number 4. So they'll hold 32 and have all the different sublevels. The next chart that I'm going to give you, because we just need to kind of get this information out there so you'll have access to it, is all about the sublevels. The table that I'm going to show you next, they're in order of filling and in increasing energy. And that's going to be important because it's going to determine how electrons enter into the different sublevels. So we're going to talk about each sublevel, the maximum number of electrons that each sublevel can hold, and the total number of orbitals. And I refer to them as orbitals, but they are those orbital orientations. So how those shapes, those mathematically drawn areas, orientations. Okay. How those shapes, those mathematically drawn areas of probability, are oriented in 3-dimensional space. So the first one, that is the easiest to fill because it requires the least amount of energy, is the s sublevel. An s sublevel can hold a maximum of 2 electrons, and it only has one orbital orientation. Remember, that's that sphere shape, and there's only one way to orient a sphere in 3-dimensional space. It always just looks like a sphere. The second sublevel, which is P, requires a little more energy, and so it will be filled second. It can hold a maximum number of 6 electrons, and it has 3 orbital orientations. So that dumbbell shape can be oriented along the x-axis, y-axis, or z-axis. The D sublevel can hold up to 10 electrons, and its orbital looks like, for the most part, like a 4-leaf clover, and it has 5 possible orbital orientations. The F sublevel can hold up to 14 electrons and has 7 orbital orientations, all of which are funky. All right, if we look at the relationship between some of these numbers, if we look at these 2 columns right here, maximum number of electrons in a sublevel and the number of orbital orientations, you will notice that the number of orbital orientations is half the amount of electrons allowed in a sublevel. And that's because each orbital can hold 2 electrons. The other one I want you to look at or notice is when we have, in our first energy level, we have an S sublevel. S can only hold 2 electrons, and so those are the 2 electrons that are allowed on the first energy level. The second energy level can hold has both S and P sublevels. S can hold 2, P can hold 6, 2 plus 6 gives you that 8 electrons on the second energy level. For the third energy level, S, P, and D, if you add all of those up, you get 18, which is how many are on the third energy level. And if you add them all up together, you're going to end up with 32 And that's how we get those numbers there. All right. Now we'll go a little bit further and get into how to do electron configuration. So the heading here is electron configuration, and electron configuration shows the number of electrons in each sublevel. Ordinarily, a sublevel is filled to capacity before the next one starts to fill. So once an S is full, then a P will start to fill. And once the P sublevel is full, then the D sublevel will start to fill. Our second rule or principle that we have to know for this chapter is the off-ball principle. The off-ball principle says an electron occupies the lowest energy orbital that can receive it. So what that means is electrons are lazy, and you should be able to relate to electrons in this sense. They don't want to have to exert any more energy than absolutely necessary. So they're going to go with the path of least resistance and enter into the sublevel that requires the least amount of energy. S sublevels have the least amount of energy, and F sublevels have the most. So this is the way they're going to fill. They're going to start with S, and then when S is full, then P will start to fill, and when P is full, then D will start to fill, and so on. So with this little bit of information, we can start to draw our atoms. Now we are going to be using this information in the table. It's just not going to be up here on the board. I'm going to start with drawing atoms. Now we're not going to draw atoms forever. I'm going to draw two, and then we're going to learn how to do electron configuration in the next video cast using the periodic table. Don't skip that one because I don't want you drawing atoms forever. It'll take too long, and the periodic table will help you out. So first let's start with an atom of carbon. Carbon has 6 protons, and right now we're just going to deal with electrically neutral, so it has 6 electrons as well. I'm going to draw my atom, and so I have my nucleus there with my protons and neutrons in there. My first energy level can only hold 2 electrons, and I'll put those 2 on there. And then no more can fit, so we have to go to the second energy level. It can hold up to 8, but I only need to put 4 more in here to get a total number of 6 electrons. So now I'm going to write my electron configuration. We're going to start off with mapping these 2 electrons right here. I wanted it to be a different color. Not going to do it. Okay, so those electrons right there. And first we're going to talk about what energy level they're on. They're on the first energy level. What is the only sublevel on the first energy level? It's S. The first energy level only has an S sublevel, so those electrons have to be in an S sublevel. And it can hold up to 2 electrons, and so we put 2 here. So this is going to become and I'm just going to use this as an example and label everything. You need to make sure you know what each of these pieces mean in electron configuration. So the big number is the energy level. The S is the sublevel. And this is the number of electrons in that sublevel. Now that part is important. When I ask you on a test, notice I said when and not if, when I ask you on a test what these numbers mean, these are the answers I want every single time. And don't tell me that this little number right here is the number of electrons, because I'm going to write where and count off points. It's the number of electrons in that sublevel. All right. So let's finish mapping out the rest of these electrons. So we had those 1s2. Those were the first ones we did. Now let's talk about these right here. We're on the second energy level, and the second energy level has both S and P. The one that's going to fill first is the one that takes the least amount of energy. That's always S. And 2 electrons can fit in S sublevel, and we have 2 to go in there. We're going to put 2. Now, let's map these last 2. I'm still on the second energy level. You have to replicate it. I don't know why I didn't make the rules. The S sublevel is now full, so the only sublevel that's left is the P sublevel. It can hold up to 6 electrons, but I only have 2 to go in there, so I'm going to put it as 2. That is carbon's electron configuration. Let's try another one. Might have to move this. Let's try argon. Argon has 18 protons, so it's going to have 18 electrons. I start with my nucleus, and then my first energy level can only hold 2 electrons. My second energy level can hold up to 8, and I'm going to have to use all of those. And notice my electrons do travel in pairs. Now I have 10 total maps, so I only need 8 more. They're going to have to go on that third energy level. All right, now I have all 18. We start at the one closest to the nucleus. We're on the first energy level. The only sublevel available on the first energy level is S, and it can hold up to 2 electrons, and we have 2 to go in there. Now we're going to map these two. We're on the second energy level. The sublevels available are S and P. S requires less energy, so S is going to fill first, and it can hold up to 2 electrons, and we have 2 to go in there. Now let's map the rest of these guys right here. We're still in the second energy level. S sublevel's full, so P has to fill next, and it can hold up to 6, and I do have 6 electrons to go in there. Now let's map these 2 electrons. We're on the third energy level, and we have SP and D sublevels. The one that requires the least amount of energy is going to fill first, so it's always S. And then S can hold up to 2 electrons, and I have 2 to go in there. Then I'll map the rest of these. I'm still in the third energy level. S is full. P is the one that's going to fill next, and it can hold up to 6, and I have 6 to go in there. So, as we're looking at these, and that's the electron configuration of argon, that's a nice little pattern. And that pattern works really well up through argon. But after argon, that pattern kind of gets destroyed because of this off-ball principle. Remember that electrons are going to take the easy way. They're going to try and go to the lowest energy orbital available. And after 3p, the next least amount of energy is going to be 4s instead of 3d. I have that down here for just a second. One thing I want you to notice. This is a map of argon. Argon has 1, 2, 3 energy levels. And if you look on the periodic table, it's on row 3 of the periodic table. Carbon had 2 energy levels, and it's on row 2 of the periodic table. Okay, so the energy levels, again, that are represented by these big numbers here, tell us the energy level. They also are going to be able to tell us what row they're located on the periodic table. All right, so after argon, there is an overlap of the principal energy levels. The next electron is going to enter the lowest sublevel, the 4th energy level, 4s, instead of 3d. Why? Because it takes less energy to do that. There's no other reason why. But we have to be able to put them in order. And it gets more complex than just that. If we look, I've got a picture for us. And there we go. Okay. So here we are with our little pattern, 1s and then 2s and 2p and 3s and 3p. All right, now comes that weird thing where we have an overlap of the energy levels. It's easier to put an electron in 4s before 3d, and so that's what an atom does. Electrons start entering that 4th energy level before they finish filling the 3rd. Then they drop back and put electrons in the 3rd energy level. Then it goes back to the 4th energy level to put some more electrons. But they don't fill it up either, and then it becomes easier to put an electron in the 5th energy level. Then it comes back to the 4th energy level and puts more electrons in there, goes back up to the 5th, drops some in the 6th energy level, comes back to the 4th and finishes filling it up, then goes to the 5th, the 6th, puts electrons in the 7th energy level, then finishes with the 5th energy level and puts some more in the 6th energy level. And really, it is extraordinarily difficult to remember this order. So the next video cast is about how to use the periodic table to help us put the electron configuration in this order. So watch that one next and on how to do the electron configuration, and it'll be a whole lot easier.